Okay, good morning everyone. So let's get started by finishing this part on adaptation on smoothness. So recall that we saw some, after seeing these general principles of posterior contraction rates, we saw some examples of prior distributions that would lead to adaptation to smoothness. So today we're going to finish this quickly and go in the direction of adaptation to other quantities like sparsity and structure in some sense. And from there, next week, we'll move on to beyond rates. We'll look into more precise, more specific properties of posteriors, more specifically credible regions and uncertainty quantification, as well as testing. Okay, so let's recall last time we learned that this one way of achieving adaptation was to take infinite series priors, right? So we saw we could take Gaussian series priors with zeta j's some IID Gaussian variables, but then we saw that it could be interesting to have other distributions, in particular that we could get adaptation with heavy-tailed priors. And then there the idea is to make both sigma j decreasing fast, okay, and at the same time the effect of this produces some smoothing, but this can be countered by the heavy tails. Okay, so when there is some signal, the heavy tails are going to pick it. And in particular, it's kind of a very Bayesian way of getting adaptation where you don't get adaptation by say, selecting a model, but rather through the qualitative properties of the distribution, here the tail distribution. Okay. So there are many other options to get adaptation to smoothness. Let me just mention a few a bit as an invitation for you to have a look if you are interested into some of these objects. There are more details in the notes, and feel free to ask questions either now or offline also on this. So one popular and very interesting class of priors is the one of spike and slab priors. I'm going to introduce those in a moment for adaptation to, they can also serve the purpose of adaptation to sparsity, so I'll not go into details here. You also have tree priors. Some of you may have heard of CART or Bayesian CART, which are partitioning algorithms. And the rough idea here, the intuition is that you select, so you have a tree of wavelet coefficients. Think of, for instance, the Haar basis, where you have indices L and K. So L would be the depth here. And with the tree prior, what you do is that you select coefficients only along a tree. Okay, you have some binary tree and you pick coefficients. So CART does actually exactly that. And so this prior has quite some flexibility. You have, this tree is random, so you may choose it. The posterior learns from the data which tree to choose, and it gives good properties for adaptation for various norms. You have also in density estimation, so let me still mention very briefly two examples. So density estimation, you may do a very popular prior is a mixture. Okay, a bit similar to kernels, like kernel estimators. Here you have you take a kernel, for instance, the Gaussian kernel, with some bandwidth parameter sigma. So of course, in the Bayesian framework, we just draw it at random. Okay, df of x, where f is some distribution that in the Bayesian setting we pick at random, right? So you have nice properties of this object, and maybe just as a little I wouldn't say spoiler, but so contrary to traditional kernel estimators, there is a nice property if you do this, is that, so you may know that for kernels, if you take a Gaussian kernel and you take the kernel estimator, since the Gaussian kernel is of order 2, okay, it's L2 moment is non-zero, then you get adaptation to smoothness up to smoothness level 2 only, okay? Whereas actually with this, if you take this as a prior distribution on densities, the corresponding posterior can be shown to adapt to any smoothness. And the intuitive reason is that, in particular beyond 2, and the intuitive reason is that you are not bound to estimate F0, you are not bound to using F0 star phi sigma, but you can use sort of, you have a richer approximation class and you can use some F1, say close to F0, but which to estimate F0. Okay, so this is just a very informal intuition. Okay, and another class which I find also particularly interesting, and that will be my last example, is that of polyetries. So I'll not define them. So it's just a way to, the polyetry is just give the intuition that it's a way to define the random distribution actually, and you can, if you choose the parameters well, the random distribution, you can actually choose it to have a density, for instance, with respect to Lebesgue measure. And in a sense, you can see it as an, again, as an invitation for you to look if you're interested. It's a bit analogous to, it's the analog in density estimation, I would say, to Gaussian processes in Gaussian regression. And one reason is you can show that they are conjugate. So if you take a polyetry as a prior in density estimation, the posterior is also a polyetry. And you have a similar kind of picture as we had for GPs. So for GPs here, if I draw here a little line with what we could call the regularity. So here at 1/2 you'd have Brownian motion. Okay, here at -1/2 you'd have Gaussian white noise. And here at regularity alpha you have, for instance, this Riemann-Liouville process of regularity alpha. You can draw a similar picture for polyetries in the world of distribution estimation or density estimation if you have absolute continuity. And here you have something at -1/2, which is very famous in statistics, called the Dirichlet process, and also in probability, I guess. And here you have, say, alpha smooth polyetries, which can model alpha smooth densities actually from on this side. Okay, so it doesn't say much, but it's just for you, if you're interested, you can, maybe I like kind of this picture as a sort of dictionary between these different priors and models. Okay, and so to conclude this chapter on adaptation to smoothness, I'd like to, and before moving to adaptation to structure and high dimensional sparsity, so let me give a little, so just a glimpse at something that you may have been wondering. Okay, since we are talking about posterior distributions, and I told you that you could use the posterior to produce perhaps to quantify uncertainty, okay, to do uncertainty quantification. You may ask, okay, can I use maybe the posterior to do adaptive confidence set? So I'm going to do an informal brief discussion. And again, I mean, it would be like a course in itself, a lecture in itself to talk about this, but just to give you an idea. We will come back to this in a certain situation where you don't have nonparametric rates, but 1/square root of n rates. We'll treat that next week. But so if you think you have a posterior on functions, okay? So one natural thing you may want to do is so you can have a look, for instance, at, suppose here you have like the posterior mean, f bar of x, and you may, it's natural to look at the ball centered at f bar, the posterior mean, and of radius r of x. So this ball B is such that, sorry, so you can try to find a ball, a radius Rx, such that pi of, so it depends on x, B of x, given the data, is equal or maybe slightly larger than 1 minus alpha. Okay, so that's what we call the credible set. Okay, so if your loss is, for instance, the L2 loss, it will be an L2 ball. If your loss is the infinity loss, it will be what we can call a band, right? So maybe from the application perspective, the most interesting loss perhaps is the subnorm loss, because you can look at pictures, okay? So what we would like to have is maybe, so here you have f bar, and maybe we'd like to draw a band around it and say that, say with high probability, the true function f naught lies in this band, okay? All right, so there are two things you want. You want coverage, so in the frequency sense, over classes of regularities, so uniformly over, so suppose I have regularity S, okay, S positive. So sometimes I noted beta, sometimes S, so here I have already an S, so let's take S. So what does it mean? It means that you'd like to have uniformly over all classes for any S and for any F naught in CS, you'd like to have that you have a credible set, meaning that the probability that the true belongs to this random ball is at least is equal to or at least 1 minus alpha, okay? And so here I could take the whole set, the set of all continuous functions, and I'd have at least coverage 1, okay? So of course the game is that you also want to have this confidence set of the small possible diameter, okay? So you'd like to have an optimal diameter plus you'd like to have it in an adaptive way, okay? Meaning that you'd like to have that the expectation under f naught of the, say, the diameter of bx is of the order, maybe up to logs, of the optimal rate. So this, say, uniformly over the class for any S and uniformly over the class CS, you'd like to have it of the order of the optimal rate epsilon n star of which depends on S. Okay, so here it would be like the one we see all the time, n minus S over 2S plus 1. Okay, maybe up to logs. All right, so that would be, you'd like to have that. And what happens, and very briefly here, is that actually, so this has nothing to do with Bayesian method. It's really an information theoretic result. This is actually impossible. So for the subnorm, it's impossible to have this. And for the L2 norm, it's only possible in certain windows of regularities. So if you assume that your smoothness is between, say, S naught to S naught. Okay? So that's just an information theoretic result. Okay? So this is a too difficult problem. And you may have a positive answer to this problem if you are a little bit less ambitious here and accept to take smaller sets of functions. So then you can have positive results, and the key here is if you assume some self-similarity, this becomes possible again. But it is kind of a sort of strong assumption. But then you may think in nature, maybe nature is self-similar, so maybe it makes sense. But it's a certain assumption. Okay, so and there are very interesting results in the recent Bayesian nonparametric literature, where there are a few results of this type. So we know we cannot solve the original problem, but if you assume self-similarity, then you can actually you have to blow up a little bit the radius of this ball by a slowly varying factor, like a logarithmic factor. But there are results by, in particular, Boton Szabo, Harry van Zanten, and Ad van der Waart, who show that you can make this program to work under self-similarity conditions. Okay, and since then, there have been a few results also in the literature. But again, this would take kind of some lectures to cover this. Yes?
Does self-similarity, does it invoke the notion of fractals or
Yeah, in a sense, you can view it a bit like this. Yeah, the intuition is that at different scales, you should have a similar behavior. You want to avoid functions that look, at certain scales, look very smooth, and at other scales, very irregular. And then, because then any estimation procedure will then not know what, in a sense, you want to do something like smoothness estimation, in a sense. And this is not possible in general. Yes?
I am not sure that I understand what is impossible exactly. I mean, I have at least two interpretations in mind. The first is that the optimal rate would be suggested by a kind of ansatz, and it turns out that no, it's not the actual optimal rate. And the other one, it would be a kind of frequentist definition of optimal rate, and no, it's impossible to attain it by Bayesian procedures.
No. So this is something that has nothing to do with Bayesian. So here, as I mentioned briefly, I mean, I just give the intuition, okay? So there is I give a little bit more in the notes, but there are some references. So here I put Bx, but actually it's any set you like, which doesn't have to be Bayesian, okay? And just to give the intuition, if you would have these true properties simultaneously, then you would be able to construct a test it's really from the frequentist perspective, okay? Because here we are analyzing also Bayesian posterior from the frequentist perspective, so it's an information theoretic result. So if you would have this, you would be able to construct a nonparametric test which would have a rate which would be faster than the minimax rate of nonparametric testing. So that's why there would be a contradiction. So the way we prove that this is impossible, and again, I don't give the details, but I'm happy to maybe we can chat a bit more in details about it. So if you would be able to construct such a confidence set, you would contradict a minimaxity result saying that the best possible rate of testing cannot be something.
Okay, but my question was precisely what is impossible? I did not get.
Okay, so it's impossible to. So, for instance, suppose you want to build a confidence band. So it's a bit the same as estimation, but now you are more ambitious. You want to build a region C of X. Let's call it C of X or B of X, such that you have both coverage. So you don't know where F naught is, but you want that with, say, probability 95%, this region C of X, this band contains the truth. So that's the first requirement. You want to have it uniformly over all possible classes of functions you are considering. And on the other hand, you also want it, so what's natural is that since you know you can estimate the truth at the minimax rate of estimation, it would seem natural that that this set can also have a diameter of the order of the minimax rate of estimation.
So when you say optimal rate on the bottom right, it's optimal for estimation, and you say that somehow the optimal rate for confidence intervals is
exactly.
worse.
Yeah. Yes. Yes.
Thank you very much.
Thanks. Yeah. Sure. Indeed. So. I mean, I didn't give, just wanted to give an informal idea, but thanks for the question, for the clarification. Yes?
So the region you are mentioning is a specific model, or what are the
So this impossibility, it's for the soup norm, and yeah, good question. So the in any model where you can find this, so as I said, it's an interplay between the optimal rate of estimation and a certain rate of testing. So in any model where you will have a certain mismatch between those rates, it will be impossible. So in all the models I talked about, it's impossible for the soup norm, like in density estimation or regression. But there is indeed the statistical model comes in. Indeed, here I wasn't talking about the statistical model, but you're right. So say Gaussian regression or density estimation.
What does the parameter S depend on?
S?
S0.
Oh, okay. So this is actually for any S naught. So, or I could call it so whatever you like. So just A positive. So here I'm not making the results precise. I just want to give you a flavor of the results. And maybe thanks for the question, because it gives me the occasion to say that you may note that since the L2 norm is weaker than the soup norm, right? So in a sense, you see here that the problems becomes a little bit more feasible, okay? And there is a natural idea which we'll take in the next week. It is that if you weaken the loss function, maybe this problem becomes simpler and simpler, and maybe at some point you'll be able to have a positive answer. And that's exactly what happens.
Does it mean if you somehow restrict the range of S instead of all S, then you can somehow make it possible?
Yes, so for instance, if you take A equals 1, then you can get, so one thing I didn't insist too much, but so it's adaptation, because if you don't ask it to be adaptive, then it's possible to build one just by taking the regularity. And so, but here, when I say this, is that then you can get adaptation in the range, for instance, 1, 2, or in the range half 1. Yeah. Yes?
Is it also interesting to consider a Bayesian type of guarantee in which we ask for this inequality to happen with high probability over our prior?
Well, so I would say that from the purely Bayesian perspective, so here you have a credibility set, okay? So if you are purely Bayesian, in a sense, you are happy with it. And so here I'm just talking about the frequentist justification of credible sets. So yeah, right. So, but indeed, so you can find sets like this. Right. Okay. So, other questions? Okay. Good. So now we'll go to adaptation to other aspects. To again see, so in this first week, the purpose is really to see that with these tools that we introduced, we can kind of cover quite a lot of different situations, and with just a few principles, like you can just keep in mind, like this prior mass principle, you should put sufficient prior mass around the point. Of course, you don't know the point, but then it means that you have to spread the mass of the prior to get a good prior. And if you want to do that, well, then you need to build a flexible prior, flexible enough so that it can cover various say regularities, for instance. And now we're going to see that you can get also adaptation to other type of parameters like smoothness, like sparsity or structure. Okay, so going to be 4. Adaptation to sparsity and or structure. Okay, so the first thing I'm going to talk about is priors in high dimensions. And before I do this, so let me just say that in high-dimensional model, it is natural to assume that you have actually a small number, or compared to the dimension at least, a small number of non-zero parameters. So the class L0S is just a set vectors such that the number of non-zero coordinates is smaller than S. Okay, so you have n coordinates and only S are non-zero. Okay, so S is called sparsity. And generally in models, I'm going to introduce a few models in a second, but generally you take S to be a little o of n as n goes to infinity, and sometimes, often we also assume that still S goes to infinity. Okay, it can be logarithmic or so that's a typical assumption. So that's called the sparsity assumption. And we are going to consider two models just to further exemplify this rate principle, rate theorem. So the first is the sparse sequence model. So very simple. It's like the Gaussian sequence model from nonparametrics, but you just assume. So here we take unit variance generally, but you could take also a sigma variance. Okay, so it's just a signal plus noise model. So xi observation is signal plus noise. So you have some background signal which you assume to be sparse. So theta is theta 1, theta n belongs to L0s for some s. Okay, so it's sparse. And here epsilon I, iid, and 0, 1. Okay, so very simple. Okay, so in this, for this, and then the loss that you take is typically the one, I mean, they are, you can take LQ losses, also interesting, but maybe the first one, the most natural one, is the L2 loss. Okay, and there the minimax rate, so let me just write it just to have it in mind, because the rate will come in the result is, if you want to estimate in this model, the best possible rate is 2 Sn, so you have even the sharp constant. So it's a well-known classical result from the early 90s that the minimax rate is of the order S. So here S is Sn. It is of the order S log n over Sn. Okay. So another model is a bit more complicated, is the high-dimensional Gaussian regression model, where you have, so here, a matrix, a vector, so that vector of observation of size n, an n by p matrix, p by 1, and here just epsilon will be n0 identity. Okay. So here you have both n and p. So here in the class L0s, you have to replace n by p. Okay. And X is called the design matrix. So here you have a sort of an inverse problem, because you want to recover theta, but you have a matrix X, and here there are some interesting, so that's called the high-dimensional regression model. There has been a lot of research since the 2000s on what kind of conditions on X. So since here you need to recover P, in principle, the situation that we're interested in statistics is actually recently, at least, is that the one where the number of variables is much larger than n, and then you need some conditions, because obviously you cannot invert if P is larger than n. So yeah, you need to understand what type of conditions are reasonable in this setting. Okay, so before going into that, let me just introduce a first class of priors. So what would be a natural prior here? So you know you have thetas have some zeros, okay? This class says that most coordinates of theta are 0. Okay, so it's natural to define a prior that puts zeros. So one natural thing is just to, on each coordinate, you flip a coin, and with certain probability you put 0, and with other probability you put something non-zero. Okay, so that's called the spike and slab prior. Okay, so the spike is because you have a Dirac mass here at 0, and here you have some called a slab, and it is, you take it to have a density with respect to the Lebesgue measure, gamma. Okay, so on each coordinate, you flip a coin, and with probability 1 minus alpha, you return 0, and with probability alpha, you return some random number that's sampled according to gamma. Okay, so that we call SAS, like spike and slab. Right? And there is a slightly more general prior, which sometimes people also call spike and slab, is the subset selection prior, where you do something slightly more general, where you just pick. So the spike and slab is obviously a special case, and here you just pick subset selection prior. You can pick first a dimension at random. So pi k would be a, or maybe pi little n, say, is a prior, a discrete prior on 0, 1 to n, prior in dimension. So given the dimension, you sample uniformly for all subsets of indices of size exactly k. Okay, and given S, theta given S is just, so on S, you just sample from, say, gamma, from the slab, and outside of S, you sample from the Dirac, so just Dirac at 0. Okay, so of course, spike and slab is just a special case where you have some binomial distribution on the prion dimension. Okay. So what can, if you analyze this in the sparse sequence model, it's very kind of neat because you can compute everything at least for fixed alpha. But we'll see in a second that, of course, we want to go beyond that because we want to do adaptation. But if alpha is fixed, you can compute everything. Okay, so you have here, of course, you can ask, okay, what is alpha? Which alpha do we choose, and what gamma do we choose? Okay. All right. So we'll go into this in a second, but so let me mention that this is just kind of a canonical prior, and sometimes from the computational point of view, so in the sequence model it's kind of okay, but in more complicated models you can still do that, but it can be, you can run into some computational difficulties, at least with the, say, usual methods, and you can also do variational base or things like that. So let me also introduce a prior for which has also been used and quite very much studied recently as a kind of relaxation, or where you replace the Dirac mass, because this makes kind of a combinatorial problem where you have to choose the subset S. You can also, a natural idea is to try to replace this by a single distribution that has no Dirac mass, but still models something like a Dirac mass with a lot of mass around 0. And something that's been proposed in the literature is a prior like this, where you have some heavy tails and also pole at 0. Okay, so it just means that the density blows up at 0, and here you have some heavy tails. And you can construct that by using a certain mixture. So a scale mixture of normals. Okay, and then lambda I is itself random with the Cauchy tau distribution. So this is Cauchy tau, means centered Cauchy distribution with scale parameter tau. Okay, so this produces something like this, where the heavy tails here are of Cauchy type. So there is a formula that I give in the note for this density. Okay. So this is an alternative to, and it will come back later today. Okay?
When you are doing the half-true prior, there is no sparsity assumption anymore. It's a way to circumvent.
Yes, good point. Yes. So when you use the horseshoe prior, you don't draw any exact zero. You still draw with high probability points extremely close to zero. So indeed, statistically, you may need some post-processing step at the end with your posterior, because your posterior doesn't produce zero. So if you want to do something like variable selection, you may have to like threshold afterwards or something like this. Yeah, sure. Thanks. Yes?
Once you have the horseshoe prior, then you draw some IID.
Yes, so it's indeed, yeah, yeah, just IID, sure. And of course, actually here, this tau has now a similar role as alpha. So you may ask, so it's IID, but then you may want to mix, to introduce some gathering strength of information among coordinates by making this guy random, actually, afterwards. So it's a bit like the alpha in the spike and slab, but I'll come to that just now. But in principle, yes, sure. So you have this. So this is a distribution, say h tau, and your law. Thanks for indeed you didn't say that. Your basic distribution then on prior on theta would just be this pi tau. Okay. Okay. So let me come back to the choice of alpha here. So maybe let me briefly talk about the case where alpha is fixed. So I'll not give the formula, but well, let me just tell you that. So if you take just pi alpha, the posterior is still of spike and slab form in the sequence model. So for now, I mean, this discussion will be in the sequence model, okay, for now, because there are already quite a few interesting phenomena that arise. And of course, one may want to understand first what happens in the simplest model before going there, okay? So sequence model. So in the sequence model, you can express, it's easy to see that this is a product. The model itself has an independent structure. So the posterior is again a product of spike and slab form. So here there is an updated weight that depends on xi. And here you have some g xi, which is a distribution that also depends on x. Okay, so it's easy to show that, and you have explicit expressions which I give in the notes for those, and those depends also on alpha, of course. Okay, but all right. So when you can look at the risk, so I'll not write it, but you can look at the rate, say, you obtain for this, and this depends on alpha, of course. And from there, you can see that the optimal rate is obtained if alpha is equal to Sn over n. Okay, so if you would know the sparsity Sn, you would set alpha equals Sn over n, and just use this prior and this posterior. You can also use, like, say, a default choice if you want to stay with fixed alpha is to set alpha equals to 1 over n. That's possible. And it gives a near optimal rate, so CSN log n. So you lose a little bit possibly in the log. So the log is, so if Sn is a power of n, you only lose in the constant. And if Sn can be quite dense, so quite close to n, you may lose in the log factor. But so this is true, but in practice, we see better results, and actually the real constants are probably much better with something that makes the alpha data dependent, okay? And so then we can just apply one of our favorite principles, okay? Either be fully Bayesian and say, okay, alpha is random, or calibrate alpha depending on the data. Take alpha the empirical base approach and make alpha hat of x. Okay. So let me discuss briefly the empirical base first. So people have done that since it's the basic model. It has been much studied, but there are interesting phenomena that arise. So there is a very nice paper, a 2004 paper by Johnson and Silverman, who studied the empirical base. So if we do empirical base here, we just follow this marginal maximum likelihood principle. So recall that if we want to do this marginal likelihood, we just have to compute. We eliminate theta in a sense in the Bayesian setting. So here, if I look at one coordinate, I have that the distribution is n theta I1, right, given theta, so which I may write theta I plus n01. And the prior, if I do spike and slab, is just on one coordinate, is 1 minus alpha, I flip a coin, delta 0, or from gamma. Okay, so here it's easy to find out what is the marginal distribution on xi. I just, so I have theta I here, which has this distribution, and I just add an independent Gaussian. Okay, so xi has just, in the Bayesian setting, it is just either, so 1 minus alpha n01, corresponding to this part, and the other part gives alpha times the convolution of gamma and the noise. Okay? So then from this formula, it's immediate to see that, so if you follow this marginal maximum likelihood principle, it suggests to take, so write the argmax over something here in a second. So you take the argmax over the likelihood corresponding to this. So it's just, so of course I have a product over coordinates. So the coordinates are independent. So product over I of 1 minus alpha phi of xi, which is the density of the Gaussian evaluated at xi, okay, because I look at the likelihood, plus alpha times g of xi, where g is just the convolution, okay, where g is the convolution of the density, the Gaussian density, and the prior. We call that gamma is the prior density. Okay, so I have a nice little formula, and here, well, we could say alpha positive, but I mentioned, I think that sometimes there are slight boundary problems. So generally, we take here, well, not on but on 0, 1, because alpha is in 0, 1. So we take here typically something like 1 over log n 1. Okay, but just for technical reasons. Okay, so if you do that, you get this alpha hat over x. Very nice. It's easy to compute. There is an R package written by Johnson Silverman that does that very nicely. You can, it's just an easy function to maximize. So you can do that up to very, very large n, like 10 to the 7 or things like that, because the model is very simple. Okay, and so then what Johnson and Silverman did is that they proved, so they were not working on the full, so from here, in our kind of philosophy, what we can do is do the plug-in posterior. Okay, so that the empirical base posterior is the pi alpha given x, where you plug in alpha hat here instead of alpha. Okay, so that's what Johnson Silverman did. But so they didn't study this subject yet. So they studied the posterior median, so coordinate-wise median. Coordinate-wise. So what is that? It's just that once you plug in the alpha hat here, okay, so if I have an alpha hat, okay, I just have a product, and on each coordinate, I can just look at the median of this distribution. Okay, so you can actually show that depending on the weight here, it's either 0 or something larger. So it's a thresholding type estimator. And they showed that the posterior median, so let's call it theta med, like median alpha hat, has an optimal rate up to a constant. Okay, so CSN. log n over Sn. 1 plus little o of 1. Okay, so that's nice. So that's for a point estimate. Okay, so that's not for the posterior, and that for slabs. So something that I didn't mention yet, maybe I should have, is that so here I'm doing the discussion with only, I'm tuning only alpha, and gamma is fixed. I didn't tell you yet what we choose for gamma. So you can show that if you take a gamma, a Gaussian is not a very good idea because the Gaussian shrinks too much. Okay, so if you take x given theta I, so the Gaussian, and then theta I and 0, 1, it's easy to see that here the posterior will be n xi over 2 1/2. Okay, so if you have a very big signal, it's not good because you'd like to keep it, and here it divides it by 2. So here it's better to have, it turns out that it's better to have at least Laplace tails. So you could have Laplace or something like student or Cauchy, and then you remove this kind of phenomenon. Of course, here we also want sparsity, so that's why we also add the Dirac mass. Okay, so the slab here they took, it can be Laplace or essentially anything heavier. There are some conditions, but it can be Laplace, Cauchy. So Laplace and Cauchy come quite often in these weeks. Yes?
Maybe I didn't hear. Why did you choose 1 over log n?
That's just for technical reasons. In general, empirical base procedures, sometimes they have little boundary problems at the boundary of the parameter space. So it is just for technical reasons. So nothing. Okay, so all right, so everything looks nice so far. But then if you look at the full posterior, so that's something I looked at with a former PhD student. We realized something is happening here is that if you look at the full posterior for the Laplace slab, so for the Cauchy slab, sorry, you get the optimal rate. Okay, the same as here. But the Laplace slab is suboptimal. Okay, so that's kind of a surprise. And let me come back to the reason why, or just give the intuition why this can maybe happen. Okay, so, but before, let me discuss the hierarchical base case. So that's something that if you do full base, so hierarchical base, so take a prior on alpha. So here, hierarchical base, we do, so theta given alpha is pi alpha, and we just draw alpha random. So again, I fix the slab. Huh? I'll discuss the choice of the slab in a second. In principle, you could also draw the slab at random, but it would kind of complexify, and in computation it would be probably a bit complicated, but there are people, actually Brad Efron, often when he does empirical base this way, he just say you take everything, you put hats everywhere, so you can also take gamma hat, but here we take gamma fixed for simplicity. And here for alpha, the natural prior is just a beta, since alpha is in 0, 1, a beta 1 n or n plus 1, because it simplifies nicely the expression of the beta density. Okay, so that's something you can do. Okay, and then you just get, so that's a prior, so that's the spike and slab. Huh? And which doesn't depend on alpha anymore. And then here it gets the optimal rate. For both for gamma Laplace or Cauchy and Cauchy. Okay, or heavy-tailed, say, like student or Cauchy. Okay, so something happens here, and maybe to give an intuition is with the empirical base approach, the only flexibility you have is in your initial choice of the prior, but once this is fixed, here you just do sort of maximum likelihood. Whereas here you have the choice of this prior. So it gives an extra flexibility, and this actually penalizes this prior penalizes more, in a sense, than empirical base plus Laplace slab. So here you see that there are some fine properties of the prior that come in. So if you do empirical base plus Laplace slab, you get something suboptimal, but playing a bit with the slab, you can still be back to an optimal rate. So if the slab is really heavy-tailed, so that's interesting. And with the hierarchical base, you actually have more flexibility in the choice of the prior on alpha. So you can compensate, even though the Laplace was suboptimal here, you can compensate for it by taking a good enough prior on alpha. And that's something we didn't prove, but I conjecture that if you put here a uniform distribution like beta 1, 1, you would have a suboptimal rate as well, because for the Laplace slab, because you'd be in a setting like this one where this uniform wouldn't penalize enough the large alphas. Whereas here, this puts, the mean of this is 1 over n plus 1, so it goes really in the direction of a small alpha. Okay, I wanted to show you this example because it kind of shows that, especially in high dimensions, interesting things can happen, and then fine properties also of the prior can be important. So the rate is not suboptimal by a lot. It's not a polynomial factor, but it's something like e to the power square root of log or something. Yes, something smaller, of smaller order than a polynomial in n, but faster than a log. Okay, so let me just give a little statement. Question? Yes?
So you mentioned the paper of Johnson and Silverman, and say, okay, they have they produce an estimator from a posterior that has the optimal rate, and then you say that.
Yes, yeah, good point, thanks. So it's an interesting thing also it gives me the opportunity to say, I forgot to say it, that here you can have a point estimator from the posterior and the posterior itself that behave differently. So here what happens is that the posterior is kind of sitting here, and the posterior median happens to be at the good place. So it can be that, so theta naught is here, the median behaves well, but the full posterior puts its mass a bit too far away. Okay, so it can just happen, okay, because the median is... No, right, exactly. And so this is precisely a setting where the posterior and aspects of the posterior can have very different behaviors. And another example, which I mentioned in the notes, but it's a good maybe occasion to mention that, is the lasso estimator. So you could have asked me, why do I bother in doing spike and slab? Why, as a prior, you don't choose prior product Laplace, for instance, okay? And why thinking about this? Because if you look at the posterior mode for this prior, it is the lasso estimator, which is known to be optimal if you choose well lambda for a certain choice of lambda. And what happens is that the problem here is that although the posterior mode is very good, it can be very good if you choose well lambda, the posterior itself is not sparse at all, and it's bad. So it's again this picture, but with the posterior mode here instead of the median. So you can, well, it's bad in terms of the spread of the mass. So the mass is spread with a radius which is larger than the radius you would want. Okay.
So why is that important to have your posterior distribution concentrated at the right?
Well, that's the goal we set to ourselves at the beginning. So, I mean, if you are happy with just a point estimate, you could say, okay, I can do that. But we want to go in the direction of, for instance, uncertain quantification and things like that. So that's why. Yeah. Yes?
if instead of alpha here, which is unidimensional, we have an information for the theta I, for example, theta I being more at zero when you go to infinite, you can put something, for example, a Dirichlet process in the alpha to be conditioned on this?
Yeah, so in principle you could do many things. Yes, so here I take the same alpha for all the xi's. So if you have some extra information or some spatial information depending on the I, absolutely you can put it in your prior. So here I just took kind of an agnostic model, like a model where you don't have structure apart from sparsity. So and I discussed this, but they are indeed you can consider more complex priors, of course. Yeah, sure. All right, thanks. So let me, yes?
For the hierarchical Bayes with
yes.
alpha, beta, so basically you're picking alpha over the 1 over n, right?
Yes.
So if you're back to the fixed alpha with 1 over n.
Well, not exactly, because here you get the exact rate with the good log.
So that's my question. Depending on the sparsity and the sparsity, like which is going to infinity as it grows, you also recover the log factors.
Yeah, so I get the good log factor here with for empirical base, and actually I didn't talk about this, but you can also get the sharp constant too, but that's another even more complex topic, but yeah. Okay, so let me just briefly state a result. So in the interest of time today, I'll just kind of give more intuitions and go quickly just about the ideas of proofs. So, but I wanted to give you, so in the notes I've tried to pick proofs that are relatively short and up to some concessions maybe on the log factors. So here is a simple theorem. So if you take a subset selection prior, okay, so this, which in particular it can be spike and slab, but here I just take this, and I assume, so just to make the connection with, so I told you already that in these high dimensional settings, maybe it's, one has to modify a little bit this, so we cannot apply directly the GGV approach or the fractional posterior approach, or I mean, maybe we can, but we have to be a bit careful with the fact that it's unbounded. So this is like a prior mass condition. So S theta naught, what it is the true support of theta. So it's the set of I such that the true theta naught, so recall I do frequentist analysis, is non-zero. Okay, so I assume this prior mass condition. And I assume also that the prior is exponentially decreasing. Okay, so d times pi nk minus 1 for d strictly smaller than 1. Okay, and then you have that, then what happens is that the supremum, so here I'll put the supremum for once, of E theta naught of pi, so theta minus theta naught smaller than constant m large enough, as usual, Sn log n. So here I'm happy with even this log n instead of log n of S over Sn, goes to 1 as n tends to infinity. Okay, so there is a quite simple proof in the notes, and I realize in the notes I kind of invoked an external lemma from a paper, but now in the version which will be available, I'll also put a little proof for a prior of this type, so this type of prior on dimension, so decreasing slightly faster, for instance, than exponential. So this is satisfied with an extra margin because of this log factor, and it verifies this. You have an even simpler proof. Okay, so let me just give the idea of proof is really to work. So when you have the base formula, so this is like the integral over b of the likelihood d pi and the integral d pi. Okay, so you have numerator again divided by denominator. And the idea is really to work in tandem for both. And the reason is that so when you work on the denominator, you'll get a lower bound, with a dependence in theta naught. So for bounded theta naughts, like in nonparametrics, usually you can remove this term, but since here we are in an unbounded, so there is no constraint on boundedness on the class of sparse vectors. So here you get something like, and here I forgot, yeah, with the Laplace. So here Laplace is nice because you can do more easily these simplifications. So e to the minus something that, so you'll get something like e to the minus, so it depends, I took Laplace 1, so e to the minus L1 norm of theta naught. And then, so that's one part of the proof. And in the other part of the proof, you have to work to get an upper bound with the same e to the minus theta naught L1 times something. Okay, so here also you get times something with the prior mass, etc. So that you can get this simplification. So it's not very difficult, especially in this model. But in more general models, also in high dimensions, you'll have, if you want to really don't have extra condition on theta naught, you have to be a bit careful. Okay, so let me see, because I'd like to talk about deep neural networks. So let me just briefly say, yes?
Sorry, I'm sure you said it, but we cannot use GGB on this because the space of parameters depends on n.
No, so that's for GGB, that's not a problem. It's more that it's unbounded. So when you have the GGB condition, you have so there are a few things that you have to. Also, the rate here goes to infinity, but that's not the main difficulty. But so remember, you have so this is the typical GGB condition, right? But here, so if there is no limit on theta naught, it's kind of clear. So I mean, just if you look in one dimension, if you put any prior, say on R, so if theta naught can escape to infinity like this, you'll get. So you know, you cannot guarantee this uniformly over theta naught. Okay, and you want to. This time I didn't. Probably on purpose, I didn't forget to put the soup, okay? Yeah, sure.
Ismaël?
Yes?
But I don't understand, because in the other model, for example, the density estimation model, you have the same kind of condition with theta naught.
No, because so in density estimation or regression, you always have something like, for instance, if you think about a subtle f, you know, so the f naught k's are always bounded. They cannot escape to infinity. Here, the only thing you have is a constraint on the sparsity. But otherwise, the theta can be 1 million or okay. So
Yeah, is the sequence F0k that is bounded?
yes, so when you look at it, when you do this for in the setting of usual settings of nonparametrics, you can see, I didn't mention that in doing the proofs, but you can see that you use, at some point you use this. Yes?
The fact that theta naught is unbounded, is it a problem if you do temperature?
Yes, it is as well. So the same problem arises. So thanks for the question. So I was going to mention now quickly the results for maybe, let me, well, I'll still write maybe, or maybe on the board, it's easier. So if you do linear regression, you can do the same. Okay, but it's a bit more complicated because you have this matrix X. Okay. So let me just give the flavor of the result very quickly. So define a matrix norm. You just take the max of the L2 norms of the columns. Okay. And what will be important here to solve the inverse problem, you need to, in a sense, to be able to invert back from x theta to theta. So one condition that is natural is related to these restricted isometry properties that are condition a bit of a similar flavor. You need to a condition like this, so to go back from x theta to theta. So you may you know that you cannot control this uniformly over vectors theta in Rp, but you may be able to control that, and indeed you can, for vectors that are sparse. So if you have a sparsity S which is little o of n, you may there are matrices that satisfy that this is bounded away from 0. Okay, and so then so I have a little theorem saying that in the notes saying that so it's actually for the fractional posteriors. So here, since the model is more complicated, I took an SSE prior, so subset selection prior, with actually Cauchy slab, and I put a condition, a mild condition on theta naught infinity, because I didn't want for the matrix model. Actually, I know proofs that do this only for Laplace type priors, but for Heavier-Tailed priors, generally in the results I know there is always some bound here because of this problem that you cannot use GGV. So this is just an informal statement because I want to move to DNNs. So the rate you get is a constant. There is the matrix norm which scales everything, C Sn. So if this omega of C Sn, the true sparsity square, is bounded away from 0, you get the rate that you want. So here I don't care about the log factor, but the optimal rate would be log p over Sn, but I'm happy here with just the log p. Okay, so there is a proof also in the notes. Okay, but in the remaining time, let me go to another type of parameter, which is what I call structure parameter, and that arises with in the setting of deep neural networks. Okay, so again, I'll discuss mostly the ideas, and you can have a look at the notes. So what is a deep neural network? So I'll just a quick introduction to this. So you have some input here, generally in RD, where D can be 10, I mean something, or 20, can be large. Okay, so you have a vector here as an input, and so it would generally draw for each. So you have some circles here, which are called neurons, and layers. Okay, so so the neural network is what's here. Okay, and here you have some output. Output, and the output is some function f x1 xd, say real valued, to fix IDs. Okay, so you start from RD. Here is the input, RD, or maybe 0, 1 to the D. Okay, and here you get the output in RD, and in the middle something happens. And so what happens? So there are two things that happen to your input signal. So the little circles, they are neurons. And here you have what's called a layer. Here is just 1 layer, 2 layers, and 3 layers. Okay, you have 3 here. DNN with 3 layers. So the depth here it's generally written as L. So that's the depth. Here is 3. Okay, and here you have certain width, so which we gather into a vector. So P1, P2, P3. Okay, so P, put a little arrow on it P of L is the width vector. Okay, the vector of width. All right, and so what happens to I didn't tell you yet. So that is, and then if you write like L comma P, it gives you a certain, what's called the architecture of the network. Okay, so you can have a very deep architecture if you make the L very big, or more or less wide, if depending on how you choose these PIs, okay? And so there are two operations. So there is an operation at the level of the neuron. So the neuron applies what's called an activation function. It's generally a very simple function, which in many relevant applications in practice, often people take just the ReLU. So rectified linear unit is just a name for x plus, okay? So just the positive part. So two operations in the network. So one is at a neuron, at each neuron, you apply the activation function. Activation, which often can be like sigma x, so x plus, so that's called the ReLU, rectified linear unit, okay? And then between layers, and also at the beginning and here, you do between layers, you have some linear operation. So you have two things actually. You have a linear operation, which is just a multiplication by a matrix. So you have something, you have matrices. So I'll write the formula in a second. You have matrices Wi. So for instance, at the beginning, you multiply your x entry by, so you take a matrix and do a Wx, and then you shift. So there are some shifts vectors, so encoded by vectors for each layer Bi. Okay. So at the beginning, you have x, you do Wx, then you shift Wx minus b, and then you apply the neuron at each specific neuron. You apply so this gives you a vector, and for each coordinate of the vector, you apply the activation function, which is fixed through the network. Okay. So let me put a formula for this. I'll just say it in words for now. So denote. So we'll have just the activation that operates on vectors. So it's just and we'll actually include the shift in there. So the shift is just before going through the neuron, but for simplicity, we'll put it here in tandem with the sigma. So sigma y1 minus v1, etc. So if you have a vector v of shifts, sigma v just means first you apply the shifts, and then you apply the activation function. Okay? So denote this, and the output now, there is a formula for the output, which is just a composition of functions, and namely a composition of these elementary operations. Okay? So I should start actually from the right. So you have x, you apply the matrix W, so that gives a vector. Then comes the first layer, so sigma v1, okay? And output of the first layer, then you have a matrix again, so W1, etc., okay? And at the beginning, so you end, of course, it's just a convention what you do, but so here I took the convention that I end with the linear operation here. Okay, so I have this. All right, so I don't have a last shift here. Okay. All right, so this is the main definition, the formula defining the output of the network here. Okay, this is given through this formula. Okay, so at the end of the day, it's a quite simple formula, but what makes things complex is that you have a composition. So with compositions in particular, you don't necessarily have very explicit expressions, so it's hard to kind of analyze directly by brute force the estimators that you get. Okay, so with the tools we have in hand now, it's going to be quite easy to define a prior on deep neural networks. Namely, we just take the quantities that show up here. What are the parameters of the network? Well, there is the architecture, and there is, given the architecture, the weights given by the matrices W. So that's called those guys are called the weights parameters. Weights, so matrices and shift vectors are called the weights. Okay, so you only need, so from the Bayesian perspective, if you want to define a prior on deep neural networks, you just put everything random. So the weights are random and also the architecture. Okay, so just to simplify a little bit, so I said that the architecture was random, but it's enough to actually take a certain type of architectures. So let's define a prior. So I'm going to fix the architecture. So the depth will be a certain logarithmic factor. I took log square. Say log factor would be fine here. And for width, I take something quite wide. I just take n. You could put something polynomial. Okay, so that I'm going to fix. You could take it random, that would make the prior more complex, but it's enough to take this. And so if you take this architecture, the number of parameters is of the order, it's not exactly this because you have to adapt a little bit at the entrance and at the output, but it's essentially of the order the depth times, so each matrix has n square parameters plus the shifts, okay, so it's of the order L n squared plus t. So this number I'll call capital T. And I'm going to define actually so in R to the power T, I'm going to define a set, the set of all possible. So if I have a certain vector in T, so I just put in this vector all my parameters in a given order. It doesn't matter. I fix the order. For instance, I say, okay, I first take all the parameters in the weight matrices and then all the shifts. It doesn't matter as long as I fix the order at the beginning. So I have my parameters here, which are, once I fix those, the deep neural network is fixed. Okay, so with here just a notation for the parameter. Okay, I put this vector theta is just the concatenation of all the numbers which are in the matrices and in the shifts in a certain given order, which doesn't matter. Okay, so pi, the prior, is going to be, so a bit like in the sparse setting, I'm going to define a sparse prior on RT. And basically what I'm going to say is that I'm going to activate to put non-zero values only on S of these coefficients of the deep neural network. So I do a bit like the subset selection prior. I draw a certain number of non-zero coefficients. Given this number, I draw a certain subset here of one uniform of a subset of 1, etc., capital T. And then given capital S, theta, my big vector of weights, I just draw it. So either delta 0 if T doesn't belong to S, and otherwise the uniform. So here what's nice is that there are some nice approximation results. Here I use some nice result in a paper by Johannes Schmidhuber on these deep neural networks. And he shows that it's enough to have to keep the parameters bounded, which is quite nice, because then you can just take a uniform distribution here. All right. So if you do that, then you get the posterior rate. So you can look at different things. The first basic result is as follows. I'm going to state two results. So one result is the following. So theorem 4.3 So if I have a function which is c beta, 0, 1 to the d, okay, with a radius k, what I get, so either in the Gaussian white noise model or the Gaussian regression model, it can be even with random design if we like. What we get is, so in the notes I proved it just for the Gaussian white noise here. In this example, we get an L2 concentration rate for Hölder functions, which is of the optimal order up to a log. So our usual rate, n to the beta over 2 beta plus 1. Okay, so that's nice. And how do you prove this? Well, the proof, I don't have much time because I'd like to talk about structure, is the key part is the prior mass where you need an approximation argument. Okay, you have seen that, for instance, for histograms, you had to approximate by a function by histogram, logically. For GPs, we have seen that the key object is the RKHS, which works with where you have to understand the approximation. And here the key is a result from this paper of Johannes Schmidt-Iber I mentioned on approximation, that you can find deep neural networks with a deep neural network with bounded parameters with an appropriate approximation for Hölder functions. Okay, so I don't, it's in the notes, don't have time to go more in details. Let me, in the maybe 10 minutes that we have, I'll talk about structure. So that's kind of a simple example, and you may say, okay, I'm happy with this. It's nice. Neural networks, they are good for beta Hölder functions, but maybe you could say, okay, I can do other methods, right? So maybe deep neural networks are good for other things. And indeed, so one thing that is a bit, okay, so here I said that I'm dimension d, sorry. So here I should add something. So the optimal rate, I didn't say that yet, but in the course, but in dimension d, you get a plus d here. And so you see if d equals 10, this rate is generally very small. Okay, so if d is large, the rate is bad. Okay, the rate can be very slow because it's a worst case rate, the minimax rate. Okay, so but what one may hope in practice is that actually, even if your input dimension is d, the effective dimension of your data is much smaller. And in particular, you may think that, for instance, either your data is sitting, I don't know, on a certain manifold or on a sphere, or depends only on certain coordinates and not on all coordinates. Then the effective dimension may be actually much smaller. Okay, so that goes in the direction of looking at functions that are compositions, compositional structures. And indeed, if you think about deep neural networks, they should be good at estimating compositions. And why are compositions interesting? So suppose your true is like this. So at first you may think, okay, it's just an extra assumption, right, that we make, and we already have this rate here for a function. So here, that would be the case where f naught is just equal to g naught, okay, and then I get this rate. But what happens is that if you look at compositions, it can be that these functions, for instance, depend only on certain coordinates, okay, and it turns out that this class is very rich and can model functions with lower dimensional structures, which you may want to capture with your estimator. Okay, so here we want to go in the direction of maybe improving this rate if we have some extra structure where here these functions, they don't depend on all coordinates, but maybe on a certain number. So I just give some basic examples. So kind of a almost trivial example is the one where f0 actually depends only on certain coordinates. Okay, so it can be, for instance, g0 of x2, or it could be g0 of x3, x4. Okay, but a priori I don't know of which coordinates it will depend on. Okay, so of course it may be not too hard if you are just in this situation to design a statistical procedure that does optimally in this case. But you have many other examples. You can think, for instance, of a function where, in fact, this function, it's a g of the sum of the coordinates, right? And then here you'd like to see that, to say that the effective dimension is what here? So here is just a number, so if I relabel it as a y, this is a function of only one coordinate, right? So in a sense, the effective dimension should be 1. Here as well, 1, here it should be 2, right? Okay. And many examples. So another example is, for instance, if your function is a sum of functions of only one coordinate. Okay. Overall, it depends on all the coordinates, but since it's a sum of simpler problems, it turns out that the effective dimension is again 1. Okay. And so the rate is maybe, the rate here is going to be something, if d is allowed to grow, is maybe d times, but if d is fixed, you just get the usual rate, beta over 2 beta plus 1, okay, instead of d. And there are many other situations. You can think, for instance, here I'm talking about coordinates, but you can just think that you, in fact, once you say, for instance, rotate the standard coordinate axis, you depend on the rotated axis. You only depend on one coordinate. You wouldn't see that if you are in the necessarily if you are in the original coordinates, but once you turn, you are. And then you just have a composition of functions where first you have a rotation, which is very kind of a very smooth function, so you should be able to estimate almost like a parametric rate, and then you have your function that only depends on less coordinates once you have rotated. Okay, and you have very many settings, so I don't have much more time to talk about it. But so two options that you have here. So in recent years, maybe in the last five or so years, people have shown that you can use here in this setting deep neural networks, like we did here. And they there is something which is in the note, which is the optimal rate for this compositional structure, which will depend on the dimension, the effective dimensions, in a sense, that you have here. So if you have an overall effective dimension, here informally d star, your rate here will depend on d star. And it can be shown that deep neural networks achieve this rate. And there is another object which I introduce quickly now, something which is maybe even more Bayesian in spirit, is a deep Gaussian process. Okay, so because I didn't have time to give a proof, a bit more insight on the proof of this, but what you do in the approximation argument is that why does it work with ReLU? Because you may think, okay, ReLU activations, they are not so smooth, right? So they are only Lipschitz. They are not more, except I mean, you can combine them so that you get just a linear function, and then it's just linear. But apart of this very specific case, it will be just a Lipschitz function and not anymore. And it's kind of curious that even if it's interesting to note that even if your output is just a piecewise linear object, it can still get the optimal rate even for larger smoothness. Okay, so here there is no restriction on the smoothness. Okay, and why does it happen is because you can approximate smooth functions by just arcs. Okay, so by linear piecewise linear functions, and this is a step in the proof that you use like a logarithmic depth to first approximate monomials, right? That we've seen in Felix's lecture, the kind of the basic object to were these monomials, but here you don't have the monomials because you have x plus. So the first step is to approximate the monomials with x plus, and then once you have the monomials, you can just approximate any function in the usual way. But you could say, okay, if I'm a Bayesian, maybe I could also replace this by, I suppose I already have done this step of approximation, and I just assume I have a Gaussian process. And since I want to be good for composition, let me just do a composition of Gaussian processes. And that's exactly what a deep Gaussian process is. Okay? And very quickly now, because I think we want to go to lunch soon, let me give just a flavor of what you can do. You can also get the optimal rate for compositional structure, so that you can adapt to structure with deep Gaussian processes. And so there are several ways you can define the Gaussian process. So here, Z of t will just be a composition of Gaussian processes. Okay. Where here you want to have processes that are multidimensional and that go from di to di plus 1. Okay, so a given process wi is in fact a collection of processes wi1, wi d, say I plus 1, okay, of t. And the input space here, t is itself multidimensional, okay? And so if you want to do something in spirit of the deep neural networks, maybe what you want to do is to allow certain variables to be activated or not, okay? Like in the deep neural network where you put some weights to 0 or not. Okay, so either you can do that. So there is a very nice paper by Johannes Schmidt-Hieber and Gianluca Finocchio in JMLR this year, Journal of Machine Learning Research, where they do the prior is, say, model selection prior, on the variables that you activate, on the variables. Okay, so this gives you a certain set S, and then given S, you do a composition, a deep GP with activated variables S. So I'm going quite quickly here, but this is the idea. In S. Okay, so that's nice. So you get the posterior, he gets the optimal rate. So the only thing maybe, so you can think that maybe you can try to, so what people do in practice is that they tend not to do this model selection prior because it can lead to, computationally it can be a bit difficult. They prefer to not select variables a priori, and just in a kind of an extra step, they then, like empirically, like in an empirical based flavor, they decide which variables to activate. So this idea kind of leads to the, so in current work with my former student Thibault, we look at deeper Gaussian processes which are constructed a bit along this idea, and the idea is that so this step is kind of optional, so it's the step where you kind of draw the architecture in a sense at random. So you can put some prior, and I'll end with that. So pi d given q. So that's in practice you could fix this in this composition. You could take, I don't know, q equals 3 or 5, and this d's to be, I don't know, 5 for instance for each. And what's important is rather here. So what we do is that we at each layer we take squared exponential Gaussian processes with certain priors on their length scales parameters. Okay, remember that for squared exponential processes, we said that we could accelerate time, right? So do this scaling of paths. So these GPs, they occur now here, dq now given also the ai's, so given aij, it will be a squared exponential. So this will be squared exponential aij. Okay, which is, again, recall that it is w of aij t if w is a squared exponential 1. Okay, so I accelerate time here if I take, if a takes a large value. And then the overall thing here, given everything, is just a composition of GPs. Okay, actually, we truncate also just so that at m, but that's just a technical point. Not write it. Okay, so there is a composition of these G's where each G is just the, so J is just the collection of the Gij. Okay, and here what I want to say is that we use both acceleration of time, and I mentioned also that you could make A very small, which corresponds to freezing the path. And that's very important here because, so we use both. So here we take what prior, I didn't say what this is. This is a horseshoe. We define horseshoe prior with parameter tau. And what it does is that it enables to have both large values, okay, which is an acceleration of time, and also small values. So you have the freezing effect. And indeed, so on those variables that will not be important, you let the prior make them very close to 0 and or to a constant. So what happens here is that if this goes to 0, this will go to w at 0. So just a constant, which means that the variable is not active in that direction. The function is just constant. Okay. Of course, it's not exactly constant, but because this is not an exact 0 with the prior, but it doesn't matter if it's very small. We get in the end the optimal rate as well, and the adaptation to the, which depends on the effective dimension d star. So we get the adaptation to structure here. Okay, and so that's work in progress with Thibaut, Henri, and Arisoa. And I'll end here for today. Thank you very much. Yes?
So for the posterior contraction rates you showed for these deep neural networks,
yes,
we had this uniform distribution.
Yes.
But do we have results for other distributions, like other choice of prime measures?
Yes, so it's enough to look at uniform, but you could look at, for technical reasons, it's easy, but you could, I believe you could adapt the results with other distributions as well. Yeah, sure. Yeah. So maybe I guess people, I mean, it's almost lunchtime, but a quick one maybe?
Yeah, it's a quick question. So if T is very large and S is small, could it happen easily that there's a lot of networks that don't output anything other than 0?
So what is C?
S. So you sample this set S uniformly,
yes,
from 1 to T, right? And then S is very small, then could it happen that it only outputs 0 for a lot of these sets?
Yes, but in principle, you hope that the posterior will correct for that, right? Okay. So yeah, so in the prior, it's just some. I didn't say actually what, but you could take a uniform indeed on dimension and something like that. Okay, thank you.